Nanofabrication is a difficult art. To practice it successfully and to develop it further, researchers need a highly controlled environment and a variety of instruments and specialty chemicals. The National Nanofabrication Center of the Center for Nanoscience and Engineering provides these to Indian researchers as they endeavor to create new nano devices and process technologies for future applications. But how does the NNFC create the precisely controlled, near-perfect conditions for carrying out sensitive processes? These could go wrong even with the minutest amount of dust, vibrations, electromagnetic interference, ultraviolet light, or other disturbances. The secret lies in several carefully designed and meticulously implemented systems and architecture, invisible to researchers in its work base. These make the NNFC what it is, a state-of-the-art nanofabrication facility comparable to the world's best. The design features that lend the NNFC its stunning contemporary profile were many months in the making. Its core design team spent nearly 3 years in planning, consulting, and detailing to outline its major constituent systems. These are summarized in a conceptual design document which served as the blueprint for the NNFC's construction over another 3 years. In this module of the guided tours of the NNFC, we will understand the design issues concerning the facility as a whole. Professor Navkant Bhatt, a member of the NNFC's core design team, will walk us around the facility, explaining what kind of nanofabrication research and processes the NNFC supports and how. As we begin the tour, let's first hear from Professor Bhatt about what happens inside the nanofabrication facility and why it is so very important.
Welcome to the Center for Nanoscience and Engineering, which houses the National Nanofabrication Center, a very unique center in the country. Today I am going to take you on a tour of Nanofabrication Center. But before that, let's understand what happens in a nanofabrication facility. In a nanofabrication facility, raw substrates of little value go through a series of processes and get transformed into a functional device or a chip. For example, the raw substrate could be a silicon wafer. In fact, silicon wafer is a very highly purified form of sand. In fact, I'm starting the tour in this location because I'm standing on a sand bed here. You see, this is the sand that you can find in plenty in the beaches in the country here. And this out here is a very highly purified form of sand, which is what we call silicon wafer. This, I'm holding a 6-inch diameter silicon wafer. At this point, this is an extremely nice mirror. Of course, it costs a lot. It's about $50 worth mirror. However, when this silicon substrate goes through a nanofabrication facility, we transform this silicon substrate into large number of chips that are printed on the silicon wafer. You know, these chips could be microprocessor chips which power the modern technology today. All the computers that you use have microprocessor chips. Each of these microprocessor chips can easily cost $500 or more. In other words, the 6-inch raw wafer, when went through the nanofab facility, has maybe 100, 200 microprocessor chips, each costing $500 or more. You see the kind of value addition that happens. In other words, there is a metamorphosis of a raw substrate into a very high value product that happens to the nanofab facility. This is what we call nanofabrication.
So, we have a brief definition of nanofabrication and we understand its significance. But can nanofabrication take place anywhere, or are there special stringent conditions a nanofab must meet, such as cleanliness?
Okay, as you can see here, this is a very large nanofab facility. It's about 140 feet along the length direction, and it's about 100 feet along the width direction, which is about 14,000 square feet of an area. And what you can see here along this wall is series of pictures which document the chronology of the construction of the nanofab. As you can see along this wall, there are very, very complex subsystems which have gone in to make this nanofab a reality. All this is required to ensure that we construct an extremely clean environment where we can do the processing of nano devices.
If cleanliness is the most important environmental prerequisite for nanofabrication, how does one measure it? And how do cleanliness levels inside the NNFC compare with other designed environments?
So all this elaborate arrangement that you have seen is to ensure that we create a clean area inside here. The entire area which is enclosed by this panel is extremely clean. This out here is a class 100 clean room. So let's define what is this clean room. When I say class 100 clean room, if I take an air volume inside such a room, which is of the volume of 1 cubic foot, if I start counting the number of particles which are 0.5 micron or bigger, I should not count more than 100 particles. Only then it qualifies as a class 100 clean. Just to give you a contrast, if you see the office area which has comfort AC, typically those are something like class 1 lakh or class 10 lakh. You will count 1 lakh to 10 lakh particle matter there, which is not at all good for making devices. Even if you see the operation theaters in the hospital or the pharmaceutical companies where they manufacture the drugs, those are more like class 10,000 clean room, whereas this is a class 100 clean room. If you go one step further, where companies like Intel fabricate the state-of-the-art Pentium chips, they are even better than class 1 clean rooms. So we need this kind of a cleanliness. Only then we will be able to construct the nano devices to be able to make an integrated circuit.
But why is there such insistence on removal of dust particles from the nanofab? What harm can they possibly do?
Okay, now you have understood the definition of the clean room. But you may wonder, why is it so crucial in a nanofab facility? Why do we need such cleanliness? Let me illustrate that with an example. You see, this is the lithography area where we transfer the patterns onto silicon wafer. What are these patterns? These are circuit layouts. Circuits where there are lots of transistors, output of one transistor should reach the input of the next transistor. Only then the circuit will be functional. What you see on that screen out there is the layout of a circuit which needs to be printed reliably onto the silicon wafer. But what you see on the other screen, on one hand, is very well printed lines, which will happen only if you have a clean environment. And on the other side, you see an airborne particle. Now you see, if that airborne particle were to be sitting on the wafer, then you will not have a continuous line. Your line will be discontinuous, which means the output of one transistor will not reach the next transistor. Your circuit will die. It's as simple as that.
So far, Professor Bhatt has introduced us to nanofabrication and its requirement for a clean environment in a generic way. Let's now understand what designing a clean room entails. It implies addressing 6 separate technical aspects as listed on screen.
Okay, now you have understood why do we need a clean room in a nanofab facility. The next question is, how does one go about designing a clean room? There are 6 important factors to be considered in designing a clean room. Number 1, what kind of cleanliness that you want to use in your clean room. Number 2, what kind of wafers do you want to process in the clean room. The third one, what kind of architecture that you want in the clean room. The fourth one, the application areas for your clean room. The fifth, the kind of equipments and processes that you want to populate inside the clean room. And the last one, the most important one, what kind of utilities that you want to supply to these clean rooms. Let's take these aspects one by one. The first one is the cleanliness. How do you decide what kind of clean room do you need? I have already told you that the industrial clean room such as Intel is typically class 1 or even better. The reason why they do such an extreme clean room is because they are worried about yield of the manufacturing. That is, if they do 1000 chips, all 1000 chips should be functional. That is why your defect density in the fab should be minimal. However, we are a research facility and hence we do not need to go overboard on cleanliness. At the same time, we need to have adequate cleanliness. And hence we decided that class 100 and class 1000 is more than sufficient for our clean room. Class 100 is the cleanest area where lithography takes place, and rest of the clean room that we have is a class 1000 clean room. The next design consideration, as I have already told you, is the wafer size. That is also a very important consideration. You see, if you look at the silicon wafer evolution, the technology evolution way back from 1960s to current technology, it has really metamorphed, starting from 1-inch diameter silicon wafer all the way to 12-inch diameter silicon wafers currently in industrial production. Just to get you a size perspective, you see we have different dimensions of silicon wafer: 1 inch, 2, 3, 4 and 6 inch. Let me show you the 6-inch silicon wafer so that you understand what kind of size we are looking at. You see, this is the 6-inch silicon wafer. As I already told you, today's manufacturing happens on a 12-inch silicon wafer, which is like a dinner plate that you use at your home. The reason why they use 12-inch is because if bigger the wafer size, you can print large number of chips on the wafer, and hence your manufacturing cost goes down. However, we are not worried about selling chips in the market, right? The bigger wafer size has a disadvantage, and that is, bigger the wafer size, the consumable cost is more, equipment cost is more, which is not really required for a research facility. At the same time, you do not want to go to the other extreme as 1 and 2 inch wafer size, which is an obsolete technology today. And hence, we decided to go with a facility, a clean room facility, which can process 4-inch wafers as well as 6-inch wafers. The other reason why we decided 4 and 6-inch is that we looked around and we recognized that in India, there are a few fabrication facilities, prototype manufacturing facilities, such as Bharat Electronics Limited, which uses 4-inch facility, Sitar and Semiconductor Complex Limited, which uses 6-inch facility. And we thought, if we come up with new technology either in 4-inch or 6-inch facilities, we can directly port this technology either to Bharat Electronics or to Sitar or to Semiconductor Complex Limited. And that is how we decided eventually that 4-inch and 6-inch wafer size is the right thing for our nanofab facility.
A clean room's layout with demarcated equipment and wafer loading areas and assigned cleanliness levels is referred to as its architecture. This is of two types.
Let's come to the architecture of the clean room. There are two broad philosophies in clean room architecture design. The first one is called bay and chase design. The second one is called ballroom design. Bay and chase design is more amenable for manufacturing facility. Here, bay means ultra clean area, which is class 1 or even better than that, and chase is an area which is abutting bay area, which is relatively less clean. It could be class 1000, class 10,000. The idea here is that most of the equipment will sit in the chase area and only the wafer loading part opens into the bay area, which is ultra clean. This is called a through wall mounting concept. So the wafer always sees ultra clean bay area, which is class 1 or better. You see, if you want to do that, you need to have all the details with you. What kind of equipments go in the clean room, what is the footprint of the equipment, and so on and so forth. This is good for a manufacturing facility because right from day one you know the entire line. However, university facilities are research facilities. These are ever evolving right from the day one, you see. And hence, we do not know what equipments will come in the future, what kind of layout will we have in these equipments and the clean room and so on and so forth. For example, what we did in our clean room is ballroom design. You see, this is an example here. The equipment is sitting in an area and the wafer loading also happens in the same area. The entire area is class 1000 area. We do not demarcate the equipment sitting area and wafer loading area, right? The whole clean room is class 1000 except lithography. But even in lithography, which is class 100 area, the equipment sitting is in class 100 area and wafer loading also happens in class 100 area. So this is the concept of ballroom design, and that is the most appropriate for the clean rooms which are continuously evolving, such as the university research facility.
The fourth factor to evaluate in designing a nanofab is the kind of applications it is meant for. Typically, clean rooms cater to either research or manufacturing.
You might ask whether all nanofabs are identical. Of course not. You see, our facility is not for manufacturing chips. Instead, it is really to conduct state-of-the-art research to be able to develop new technologies, new prototype devices for future nanotechnology applications. Although the industrial foundries can be more sophisticated and also more expensive and automated, in my opinion, it is relatively easy to design clean rooms for industrial facilities. For example, as soon as you say that I want an industrial facility to be able to manufacture 45 nanometer CMOS technology on 12-inch diameter silicon wafers, all your boundary conditions are very well defined. You know exactly what is the details of your process line, what kind of equipments will go in, what kind of utilities will be there, and you just need to execute the standard design. But on the other hand, university research facilities are quite different. In fact, it is very difficult to predict the research trajectory in the next 10 to 20 years down the line. As a matter of fact, you have not even hired faculty members who might come on board 5 to 10 years down the line with completely new radical ideas and devices and process design, so that you should be able to accommodate such radical things. In other words, you need to create in an university an extremely flexible facility which can be made adaptable 5, 10, 15 years down the line. At the same time, it should satisfy the current needs.
Broad-based research at the NNFC employs a variety of processes and equipment. An important task is therefore to partition the clean room for specialized functionalities.
I'm sitting in the BMS room of the clean room, which houses the building monitoring system. I thought this is a very good place to explain more details about the clean room design. You have understood that our clean room has a ballroom design concept. The next challenge that we have is to functionally partition this clean room to be able to do different processes on the silicon wafer. You see, this is our clean room layout. The user would typically come in through the gowning area and enter into the central clean room corridor. You see, on both sides of this corridor, there are functional partitions. And on the other end of the corridor, there is a lithography area. The lithography area occupies almost 25% of the clean room. And the functional partition on the two sides consists of areas to etch films from silicon and areas to put films on top of silicon. As I mentioned, this is a building monitoring system, and hence we have the screen which shows the real-time surveillance of the clean room. You see here the lithography, which we call yellow room, which is the most sophisticated area in the clean room, because this is where we need to have extremely tight environmental conditions. The temperature here has to be controlled within plus minus 1 degree centigrade, and the humidity here has to be controlled within plus minus 5%. So that is a very, very controlled ambient. And there are a couple of other important areas that I wanted to highlight in terms of the design consideration. You see, I already mentioned that our clean room is a very flexible facility. We do CMOS process as well as MEMS process. One of the challenges that comes in is to avoid cross-contamination. For example, let's look at the wet process area. You see, one of the chemical that we use here is potassium hydroxide, which is extremely essential for MEMS processing. However, it's a no-no for CMOS processing. So we have to ensure that there is no cross-contamination. What we have done is we have isolated the wet benches which do MEMS processing and the wet benches which do CMOS processing. Right? So this is something that you need to go into the details when you do the design. There's one other item that I want to highlight is something called in-house equipment development. Typically, you buy equipment from various commercial vendors to be able to do processing of the silicon wafer. But at times you will find that there are no commercial equipments available in the market. Then we would like to be able to develop equipment in-house here. We do have expertise to be able to do that. For example, this equipment that you see has been completely developed by one of our colleagues inside this clean room, which is not commercially available. As a result of that, we can do new kinds of processing which would have been simply impossible if we had not done this in-house equipment development.
NNFC equipment make use of several specialized utilities during the workday. Designers of the clean room have to meticulously tabulate their usage and points of need in a utilities matrix.
Now we are in the mezzanine floor of the clean room, which houses a very large number of utilities of the clean room. So what are these utilities? For example, there are two kinds of water that we use in this clean room. One of them is called chilled water, which is a very cold water, of the order of 10 to 15 degrees centigrade temperature. And the other kind of water is extremely pure water, which we call deionized water. In fact, the resistivity of this water is 1,000,000 times higher than the usual water that we drink. So much so that we have extracted out all the ions from this water. And hence, it is not safe to drink this water, although it is so pure. And similarly, we have two different kinds of vacuum. One of them we call process vacuum, which is required to hold the wafer, and the other one we call house vacuum, which is required to clean the clean room so that we maintain the clean condition. And then we have three different kinds of gases. We have what is called toxic gases, which are extremely harmful for our life. We have pyrophoric gases, which will just turn into flame as soon as they come in contact with the atmosphere. And we also have corrosive gases. In fact, we use 30 different kinds of gases in this clean room. So the idea of utility matrix is really to identify the fact that we have these large number of utilities. Where will you take these utilities inside the clean room? Not every room will need all these utilities. Hence, we come up with what is called a utility matrix, which shows here along the column different functional areas in the clean room and along the rows which are different utilities. This is what is called a general utility matrix. And in addition to that, you have what is called a specialized gas utility matrix. All these crosses here show which of these utility goes into which of the functional area. Right. So this is a very important task, and we spent quite a bit of time to come up with this utility matrix. So I will show you an example of the actual routing of the utility. For example, in this mezzanine floor, we have what is called a plenum of the clean room, which is this area that we see out here. What you see here, for example, is a large number of gas lines. All these pipes take different kinds of gases. And what we do then is we decide, okay, I have a diffusion area over there and only these number of gases should go down. And I have an equipment development area out there and only a different number of gases should go down. And that is how, based on this utility matrix, I route all my utilities to different areas in the clean room.
2 years of top-level design comprising all the 6 factors provided a clear view of the NNFC's desired features. Yet, Another 2 years had to be spent to flesh these out in a conceptual design document to invite construction bids.
So we spent more than 2 years in order to come up with the details against all these 6 aspects. However, that was still not sufficient to call for tenders for the construction of this clean room, because you needed a very detailed document which can be used as a basis for calling for tenders. So then we decided to engage a UK-based company called Felcon to come up with what we called a conceptual clean room design document. So we, a core clean room design group from IISc, along with a few engineers in Felcon, worked for another 2 years, and this went through very intense discussions and debate, and all that culminated finally into what we called a conceptual clean room design document. You see, this design document has all the details on the layout drawings of various aspects of the clean room and a very detailed description of what goes in every module in the clean room. And then, based on this document, we called for a competitive tender process, and through competitive bidding, we selected a company called Ellipsis, which is based out of Singapore, and we awarded a clean room construction contract to Ellipsis. Then, although this was a turnkey clean room construction, we had to make sure that they do the good job, and this was ensured by a very careful monitoring day in and day out. So in other words, we started this whole process 7 years ago. It took us about 2 years to come up with some details of various 6 aspects, and another 2 years in order to be able to come up with a conceptual design document, and another 3 years to ensure that we monitor this clean room construction day in and day out. In other words, in the last 7 years, we have spent a large amount of our time to ensure the clean room construction happens properly. In the process, we have sacrificed our research time, our family time, and so on and so forth. But you see, looking back, all this seems really worth it, because now you have one of its kind state-of-the-art nanofabrication facility, which can compete the very best facilities in the world.
On this tour, Professor Navkant Bhatt acquainted us with the design features of the NNFC as a whole. To learn more about other specific design aspects, please watch the remaining videos in this educational series. Thanks and goodbye from the NNFC.